Welcome to solverfy.
6.17. So we have 2 point masses of mass big M here, sitting out somewhere in space. They're separated by a distance of 2r, capital R. Then we have another mass here that lives on the perpendicular bisector of the line connecting these at some distance x away. And we want to show that the force on little m here as a function of x is this, and that it's always directed towards the other two masses. So we can actually figure out the direction of the force just from what's going on here with the geometry of the problem. We know that because this is always the same vertical distance above at the little m as this one is below it, that the force has to be entirely along the x-axis. And because we know that gravity is attractive, that it has to point towards the masses that are causing the attraction. So we've got the direction basically settled. So now if we consider the force from one of these, we call it F1 or something maybe, we have the distance here is the square root of x squared plus r squared. So this is going to be g times the product of the two masses divided by the distance squared. So actually just x squared plus r squared. Now we want the x component of this, because the y component from either big mass is going to cancel out. And so to do that, we just have the cosine of theta multiplying that, where here's theta. And we know that the cosine of theta is the adjacent over the hypotenuse. So this is g big M little m over x squared plus r squared times the adjacent x over the hypotenuse, the square root of x squared plus r squared. And so the x component of the force from one of the masses is g big M little m x. So this is the square root of x squared plus r squared squared. So we have the square root to the third power of x squared plus r squared, which is more typically written as just x squared plus r squared to the 3/2. And so the net force, since we have two of these, is going to be 2 times the x component we just found. So it's going to be 2g big M little m x over x squared plus r squared to the 3/2, which is what we were hoping to find.